All right, it's 6:35, so I'll start now. Hello, everyone, and welcome to today's Logisum Math Workshop. I'm Christopher Teo, and today I'll be going through some combinatorics problems from the PUMAC, a math competition hosted by Princeton University. And I see some of you have asked, what is combinatorics? Well, combinatorics is an area of mathematics very related to counting and finding properties of these structures. And you'll see what I mean in a second. And many of the combinatorics problems you'll see in the PUMAC and other math competitions deal with enumeration, where you want to find how many ways you can do something. And we'll take a look at some of those problems today. So let's get going. So I'm going to show you guys the first problem for today. And I'll give you guys around 5 minutes to think about it yourself. And if you have any questions, let me know. And after those 5 minutes, I'm going to go over a solution of this problem. And we'll do that for 5 or 6 problems for today. So you guys can start reading the problem. And in 5 minutes or so, I'm going to start showing you guys a solution. All right, you guys have 1 more minute until I start going over the solution. All right, I'm going to start going over the solution. First of all, the answer is 111110. And so great job to those people who got it right. And now I'm going to explain how we got this answer. So let's first read through the problem together and see what this problem is actually asking. Reading through a question carefully is very important in combinatorics problems and basically word problems in general. So yeah, so we have this person Rooney, who is speaking his made-up language, Rooney's, that consists of only the letters zap, zep, zip, zop, and zup. And so first of all, we don't really need to call these things these weird names. We could just change them to A, E, I, O, U, just to keep things simple. And okay, words in Rooney's consist of anywhere between 1 and 5 letters inclusive. So a word can have anywhere between 1 and 5 letters. That one's pretty self-explanatory. And Rooney can choose to add emphasis on any letters that he chooses in a given word, hence making it a totally different, distinct word. So what this means is in any letter in any word, he can choose to add emphasis on the letter, and this would make it a different letter effectively. So in fact, in English, we have this structure where we take a letter and we add emphasis on it by, or not exactly emphasis, but we kind of use it differently. We write it differently when we have a capital letter versus a lowercase letter. So in fact, as for these letters, we could just call them capital zap, and we can write them in this way by writing them as capital A, capital E, capital I, capital O, and capital U. So in fact, in Rooney's, we can put any of these 10 distinct letters in any order you want to form a word. And so, for example, if you have a 1-letter word, there is exactly 10 to the first, which is 10 ways to create such a word. And if you have a 2-letter word, there's going to be 10 squared, which is 100 ways to create the word, because there's going to be 10 ways to choose the first letter out of these 5 lowercase letters and 5 uppercase or emphasized letters. And then there's going to be 10 cubed ways to create a word with 3 letters, 10 to the 4th ways to create a word with 4 letters, and last but not least, 10 to the 5th ways to create a word with 5 letters. So in total, there's going to be 11110 ways to create any word with anywhere between 1 and 5 letters inclusive. So this is the total number of possible words in Rubiks. And this number is our answer. So are there any questions? All right, if there are no questions, let's move on to the next problem. So again, I'll give you guys 5 or so minutes to think about this problem before I start going over it. All right, I'll be going over the solution in around 30 seconds. Okay, I'll be going over the solution now. So first of all, the answer is 8,640, and good job to those of you who got it right. And so let's go over first, let's first read through this problem. So Joey is playing with a 2x2x2 Rubik's Cube made of 8 1x1x1 cubes with 2 of these smaller cubes along each of the sides of the bigger cubes. So we're going to have a cube that looks something like this. And those of you who have played with Rubik's Cubes probably have a good idea of what this looks like. And so we have 8 of these cubes, 8 of these little cubes. And one day, Joey accidentally breaks the cube. And he decides to put the cube back together into its solid state by placing each of the unit cubes back one by one. And he is only able to put in a unit cube if it's adjacent to a unit cube he already placed. And if different orderings of the ways he chooses the cubes are considered distinct, we want to determine the number of ways he can reassemble the cube. And so what he's going to do is he's going to start with one cube, one of these 1x1 cubes, and he's going to start attaching them back on, the other cubes back on. So let's say, suppose he starts with this cube. Then there are 3 other cubes that he can place onto, that he can reassemble next. And those are the 3 cubes that are adjacent to this cube, which are the one on top, the one to the right, and the one to the back of this cube. So first of all, there's 8 choices for which cube Joey picks up first. So that's going to give us 8 choices. And as for the second choice of a cube, the 3 choices that we have are the ones that are adjacent to the first cube he chooses. And so there's going to be 3 ways to choose our second cube to reassemble. And so now, let's just say that he chose this cube. So he's reassembled these 2 cubes, and now he has 4 more cubes that are adjacent to these 2 that he can try to reassemble next. And these 4 are the ones on top, the 2 on top, and the 2 to the back of these 2 cubes. So there's going to be 4 ways to choose what cube he's going to reassemble next. And you can see that no matter which 4 of these cubes that he chooses next, he's going to end up with an L-shaped figure that kind of looks like this. And now he can choose whether to reassemble this cube next or the other cubes next. Oh yeah, and don't forget to add the multiplying by 4. And next, we're actually going to have some casework based on which cube we reassemble. So if we reassemble this cube, per se, then we're going to have an entire face of this 2x2x2 Rubik's Cube reassembled already. And no matter what order he reassembles the remaining 4 cubes, it's going to be a valid reassembling because each of these 4 cubes is already adjacent to one of the cubes he already assembled. So if we choose this cube, this 1x1x1 cube as the next cube that he is going to reassemble, there's going to be exactly 4 factorial ways to reassemble the remaining cubes, which are these 4 behind the original 4. And the other case is if he decides to assemble one of the other cubes. So they are this one, or just these three. And so if you go through each of these possibilities, you can see that if he chooses this cube, there's also going to be 4 factorial ways. So let me just write it this way. If he chooses this cube next to reassemble, all the other 1 by 1 by 1 cubes are already adjacent to at least one of these cubes he has already assembled. And so he can reassemble these cubes in any order. So that's going to give us another 4 factorial. And he can also assemble the cube behind this one. And that's going to give us another 4 factorial, because all of the cubes in the 2 by 2 are adjacent to at least one of these 4 cubes that we've already assembled. And the only other possibility is if Joey decides to reassemble this cube next. In this case, we must choose from one of the 3 cubes that are adjacent to the ones we've already picked. So for a second, let's just ignore these boxes and just consider the centers of these cubes. And by considering it this way, we can visualize the cubes in the back as well. So each of these vertices of this cube containing the centers of each of these 1 by 1 by 1 cubes denotes one of these 1 by 1 by 1 cubes. So vertices that are connected by an edge are adjacent in the 2 by 2 by 2 cube. And so we have already assembled these 4 vertices, or 1 by 1 by 1 cubes. And we want to reassemble the remaining 4 vertices such that each cube he places next is adjacent to at least one unit cube he already placed. So the 3 cubes he can place next are these 3. And in the original diagram, that is corresponding to this cube, and the last unshaded cube in the bottom face. And so there's going to be 3 ways to choose our next placing. And let's just say we place our next cube over here. Then all of the 3 remaining cubes can be rearranged in any way we want, because they are already all adjacent to at least one of the cubes we already placed. So there's going to be 3 factorial ways to basically reassemble the remainder of the cube from here on. So this, through casework, is the number of ways we can reassemble the cube. And we can just calculate this out. And then we get that the answer is 8,640. All right, if there are any questions, please let me know. Okay, I haven't been getting any questions, so let's move on to the next problem. So as usual, I'll give you guys 5 minutes. Somebody's asking, what is collinear? So 3 points in a plane are collinear if they lie on the same line. So for example, the points 1, 5, 2, 7, and say 4, 11 are collinear because they all lie on the line y equals 2x plus 3. And somebody's also asking, what does degenerate mean? So degenerate triangle means a triangle where all 3 vertices lie on the same line. And it's typically not considered a triangle. But in this case, we're considering 3 points in a line as a degenerate triangle, which has area 0. Right, and before you guys continue, I'm just going to introduce to you a very helpful formula for this problem. And this is as the shoelace formula. And for this specific problem, we're going to consider the shoelace formula for triangles. And so what this says is that if we have a triangle with these 3 vertices, where A1, B1 is A2, B2, and A3, B3 are points in the plane, the area of the triangle made by these 3 points is 1/2 the absolute value of this thing. And as you can see, there's a lot of shifting going on. We start with A1, B2, and then we shift to A2, B3, and A3, B1. And then we subtract A2, B1, A3, B2, and A1, B3. We're kind of going the other way around this part. So this is going to be helpful in our in solving this problem. So around 2 more minutes, and we'll go over the solution. All right, let's start going over the problem. So The question asks us to find the probability that the area of a triangle with vertices who are integer coordinates between 1 and 2020 inclusive, that this triangle bounded by these three vertices is an integer. And so first of all, this is not always true, because, for example, if we have the three vertices 1, 1, 1, 2, 1, and 1, 2, this triangle has area 1/2. And so this is a triangle that does not have an integer area. But there are examples of triangles with an integer area. And this is also easy to find just by taking 1, 1, 3, 1, and 1, 2. And here we have a right triangle with base and height 1 and 2. And this area is going to be 1. So this is an integer. And so we can use this formula, the Shoelace formula, to determine whether the area of a triangle with these three vertices is an integer. And from this formula, we can see that since a1, b1, a2, b2, a3, b3 are all integers, this area is going to be an integer if and only if this expression is even. And so we want to determine when this expression is even. And in fact, we want to determine how often or how likely it is for this expression to be even. So let's rewrite this equation in this way. And so here we kind of isolate the a's from the b's. And we also get something interesting from the b's. So we can rewrite this equation, this expression into this form, where we have a1 times this thing, plus a2 times this thing, plus a3 times this thing. And these three things sum to 0. Since b2 minus b3 plus b3 minus b1 plus b1 minus b2 is 0, since the b1s cancel out, the b2s cancel out, and the b3s also cancel out. So we're going to perform casework on how many of a1, a2, and a3 are even. And in fact, when a vertex has an even coordinates, we can consider it as 0, and if a vertex has an odd coordinate, we can consider it as 1. And the reason we can do this is because we're only considering the parity of this expression. So it doesn't matter whether you have 0 or 2 as b1. It's not going to make a difference in the parity of this expression. So in other words, we can just pretend that all of the coordinates are 0 or 1. In fact, we can do this because we're equally likely to get an even coordinate as we are to get an odd coordinate, because there are 1,010 even coordinates, or rather, there are 1,010 different possible even coordinates, and there are 1,010 different possible odd coordinates. And so 0 and 1, or even and odd, are equally likely. So let's write out our cases. So the first case is if we have 0, 0, 0. Our next case is if we have 0, 0, 1, 0, 1, 0, or 1, 1, 0, 0. And we'll consider this all the same case, because there's going to be exactly the same number of ways to pick b1, b2, and b3 by symmetry. And we also have 0, 1, 1, 1, 0, 1, 1, 1, 0. These are all also considered the same case, since we have 2 1s, and the number of ways we choose b1, b2, and b3 won't change between any 3 of these cases. And our last case will be if we have 1, 1, 1. And just for a sanity check, we should have 8 cases, because there are 8 ways to select A1, A2, A3 to be either 0 or 1. Let me just format this a bit. And now let's go through each of these cases. In fact, there's only 4 unique cases, and the others are just copies of other cases. So let's go through the first case first. If A1, A2, and A3 are all 0, what is the probability that if we pick B1, B2, and B3 to be anything from 0 or 1, that the sum is even? And so we can notice that if A1, A2, and A3 are all 0, then this expression is just 0. And then, since 0 is even, this is always true. So yeah, as Jennifer said, the probability here is exactly 1. And let's move on to the next case now. If A1, A2, and A3 are 0, 0, and 1, what happens? If A1, A2, and A3 are 0, 0, 1, then the first two terms become just 0, and the third term becomes B1 minus B2. And we want this thing to be even. So what's the probability of B1 minus B2 being even? So either we want B1 and B2 to be 0, or we want B1 and B2 to be 1. Because otherwise, B1 minus B2 is going to be either -1 or 1, and those are both odd. And in each of these cases, there's exactly 2 ways to choose B3. So this will give us a total of 4 ways to choose B1, B2, and B3. And so since there are totally 8 ways to choose B1, B2, and B3 just randomly, and 4 of those ways give us an even product, the probability of getting an even product given these 3 values of A1, A2, and A3 is 1/2. And you can argue something similar for the next case, which is if we have 0, 1, 1 as A1, A2, A3. If we have 0, 1, 1, let me just erase this. If we have 0, 1, 1, then we can rewrite our expression as B3 minus B1 plus B1 minus B2, which is B3 minus B2. And in order for this expression to be even, we need to have either B2 and B3 both equal 1, or B3 and B2 both equal 0. And again, there's going to be exactly 2 ways to choose B1 in either of these cases. And this is going to lead us to the same probability of 4/8, which is, again, 1/2. And our last case is if we have A1, A2, and A3 all equaling 1. And if you plug it back into the expression, we see that if A1, A2, A3 are all equal to 1, then we have B2 minus B3 plus B3 minus B1 plus B1 minus B2, and this sums to 0. Since this sums to 0, our expression is already even. And again, the probability that the area is even is equal to 1. So, all right, we're really close to being done. We have these 8 cases, each of which has 1/8 chance of occurring. And we can sum these up. We can sum up all of these probabilities. There's a probability of 1 that we get an integer area if we have A1, A2, A3 all being 0, or in other words, all being even. And then there's a half probability if any of these 3 cases occurs, and also a half probability if any of these 3 cases occurs. So I'm just going to write it for the sake of simplicity as 1/2 times 3 times plus 1/2 times 3 plus 1. And this is going to give us a final answer of 5/8. giving us the final answer of 13. All right, so are there any questions? If there are no questions, let's move on to the next problem. So as usual, 5 minutes. So just as a prologue to the solution of this problem, something very important in this problem and many other problems is to draw a visualization of the data that we're given. I'll start talking about the solution in around 2 minutes. All right, I'll start to go over the solution around 10 seconds. So, okay. So first of all, the answer is 79,200. So good job to those of you who got this answer. And let's start. So we have 6 distinct coins in a jar, and we're going to take out 3 coins at a time and add a dot to each of these coins. So let's say these are our 6 coins. After we add a dot to 3 of these coins, 3 of these coins are going to have zeros, and 3 of these coins are going to have ones, as in 0 dots or 1 dot. And we want to find the number of orders that Carrie could have chosen the coins 3 at a time, so that eventually, for each number in 0 through 5, sum one coin, so a coin out of these 6 is going to have I dots on it. So we're going to end up with one coin that has 0 dots, one coin that has 1 dot, and so on until one coin that has 5 dots. So first of all, in the way the problem is stated, we don't really know which coin has 0 dots or which coin has 1 dot, 2 dots, and so on. So we're going to first order the coins. Let's just say that the first coin is the one that has 0 dots on it. The second coin is the one that has 1 dot on it, and so on and so forth until the sixth coin is the coin that has 5 dots on it. And in fact, there's 6 factorial ways to permute this, because it's also possible that, say, the first coin has 4 dots on it, the second coin has 2 dots on it, for example. And so this is just giving order to these coins that we're considering. So there's 6 factorial or 720 ways to permute the coins, so that the first coin has 0 dots, the second coin has 1 dot, and so on and so forth. So the way we're going to visualize this is by drawing out a table that represents which coins are chosen at which step. So here are our 6 coins: 1, 2, 3, 4, 5, and 6. And the number of coins they have at the end are 0, 1, 2, 3, 4, and 5. So these are the totals. And as for rows, what we're going to do is say in the first occasion, he takes out these 3 coins, 1, 3, and 4. Then we're going to put 1 in each of these three coins and zeros in the other coins. So we're going to have 1, 0, 1, 1, 0, 0 as our signature for this row. And if we do this over and over again, we're going to get a grid where the sums of the columns are 0, 1, 2, 3, 4, and 5, and the sums of the rows are all 3. Because each time, on each occasion where he takes out 3 of the coins, he's going to take out exactly 3 coins. And so we basically have this table, and we want to enumerate the number of ways to create this table such that the columns have sums 0, 1, 2, 3, 4, 5, and the rows have sums 3, 3, 3, and so on. So how many occasions will there be? So how many times is he going to take out 3 coins? So every time he takes out 3 of the coins, he adds 3 dots in total. And at the end of the process, there are 0 plus 1 plus 2 plus 3 plus 4 plus 5, which is 15 dots, which means that there has to be exactly 5 times that he takes out 3 of the coins. So this process is going to take him 5 steps. And now we have our entire 5x6 grid full of zeros and ones. And so first of all, one thing you can immediately notice is that all of these things have to be 0, since this sum is equal to 0. And also, all of these things have to be 1, because the sum of this column is 5. And next, we can notice that no matter which of these 5 places we place the 1, let's say we place the 1 here, there's going to be exactly the same number of ways to place a 1 anywhere else, for say here. So we can choose one of these five positions to place a 1 in this column. And so there's 5 ways to enumerate this. And then what next? So in fact, we're going to consider this column next, specifically the column with 4 dots. And so there's going to be exactly one place that has a 0, where all of the other 4 cells in this grid have 1 in it. So we want to do casework on where the 0 is. And we see that if the 0 is here, or if the 0 is here, or if the 0 is here, or if the 0 is here, it makes no difference. So in fact, we have 2 effectively different cases. So the first case is if we have a 0 in this position. Then these 4 are all 1. And there's only one way to do this. And then for columns 3 and 4, we need exactly one 1 in each row. So for example, if we have a 1 here and a 1 here, then these 3 have to be 1. So we're going to choose 2 places where we're going to put 1s in the third row. Sorry, the third column. And let's just say we place those 1s over here. Then the remaining ones in these 2 columns have to be here, here, and here. And so the number of ways this is going to happen is exactly 5 choose 2. And this is the number of ways we just pick 2 of these cells out of these 5 where we place 1s. And then wherever we place 1s in the 4th column are also determined. And everything else is filled in with 0s. So the other case is if we place the 0 somewhere here. If we put the 0 here, or any of these other places that do not coincide with the row that already has a 1, then there's going to be 4 ways to choose where the 0 goes. And then we want to consider the number of ways we can fill in column 3 and column 4. So first of all, these 2 have to be 0 because we already have a sum of 3 in the first row. And both of these have to be 1 because if one of these is 0, then this row is going to have a sum of at most 2, and we want the sum to be 3. So this forces these 2 cells to be 0 and these 2 cells to be 1. And out of these 3, out of the 3 remaining rows, we need, or out of the third column, we need one of these 3 cells to be 1, and the other 2 would be 0. And no matter which one of these 3 cells you pick, there's going to be exactly one way to finish off the grid. So in fact, we multiply by 3 here. And this is going to be the number of ways to fill in this grid. And we can calculate this as 110. And to find the final answer, we must remember to multiply by 720, which is the number of ways to permute the coins so that we can get this grid in the first place. And so that gives us a final answer of 720 times 110, which is equal to 79200. And that's our final answer. Okay, are there any questions? If not, let's move on to the next problem. I'll give you all around 5 minutes to think about it before I start going over the solution. And as usual, remember to read the problem carefully. All right, it's been around 5 minutes, and I'm going to start going over this problem. So it's quite a long statement, so let's read through this carefully. So Gary is baking cakes one at a time. However, Gary has not been having much success, and each failed cake will cause him to, unfortunately, slowly lose his patience until he eventually gives up. So initially, a failed cake has a probability of 0 of making him give up. Each cake has a 1/2 chance of turning out well, with each cake independent of every other cake. So his previous cakes do not affect the making of his next cake. And if 2 consecutive cakes turn out well, the probability resets to 0. This is referring to the probability that he gives up following a failed cake. And on the other hand, if the cake fails, assuming that he doesn't give up at this cake, his probability of breaking on the next failed cake goes from p to p plus 0.5. So first of all, this probability can only go up by increments of 0.5 or get reset to 0. So basically the only 3 possibilities for this probability are 0, 0.5, and 1. And the question is asking us if the expected number of successful cakes Gary will bake until he gives up is p over q. Find p plus q. All right, so we're going to use a method called states. And what we're basically going to do is, let's say the expected number of successful cakes Gary will bake until he gives up, given that his current probability is 0 and he's not he's just starting off. In other words, either he's starting off, this is his first cake, or his probability was just reset to 0 on the last cake. So we're gonna call this expected value E0. And let's see what happens. If in his first cake, it turns out that he fails, we're gonna call it a loss, then the expected value of successful cakes Gary will bake will be 0 plus E 0.5, where E 0.5 is the expected number of successful cakes Gary will bake until he gives up, given that he has a probability of 0.5. And since after the first cake, which failed, his probability of breaking on the next failed cake is now 0.5, our first term is going to be 1/2 times 0 plus E 0.5. And we have 2 more cases. The second case is if he first wins, or if he first succeeds on making a cake and then fails on making a cake. And so in this case, his probability doesn't reset to 0 since he didn't get 2 successful cakes in a row, but his probability actually increases by 0.5 because he failed on the second cake. But in this case, he succeeded in making his first cake. So that's 1 successful cake that he has made. And as for the remainder of the cakes, he's going to get an expected E of 0.5 cakes. And then in the third case, if he has 2 wins and he bakes both of these cakes successfully, then he's going to reset to 0. So we already have 2 successful cakes. So in fact, the expected number of successful cakes that Gary will bake in this case is 2 plus E0. So that's our first equation that relates the expected values of the number of cakes he bakes, given that his probability is 0 or his probability is 0.5. And we're going to do this again for E of 0.5 as well. If he loses on his first cake, he's going to gain 0 cakes, 0 successful cakes, and there's also a probability of 1/2 that he gives up. But if he doesn't give up, which also has 1/2 probability, he's going to face a probability of 1 that he breaks on the next failed cake, because his probability goes from P, which is 0.5, to P plus 0.5, which is now 1. So this is the expected value of this expected number of successful cakes Gary will bake until he gives up in this case. And our second case, if he wins on the first cake and loses on the second cake, he's going to gain 1 successful cake. And again, he's going to either give up on the second cake, or he's going to continue on the second cake for 1/2 probability. And the expected number of successful cakes Gary will bake if he gets to the probability of 1 is E1. And then our third case is if he wins on both cakes. And in this case, he already gained 2 cakes, and also he resets to 0. So he's happy. So this is our second equation. And as you can see, we have 3 cases as in the first one. And we're going to do the same thing for E1. And now you can see how we kind of get a system of 3 linear equations in 3 variables. And so we're going to be able to solve this system of linear equations and find E0, which is what we want to find. So let's finish up this last equation. If he loses on his first cake, then he gives up, because his probability of giving up is currently 1. So he's going to gain no cakes. If he wins first and then loses on his second cake, he's going to gain 1 successful cake, but he's not going to be able to get any more cakes because he's going to give up on his second cake. And in our last case, if he wins on both cakes, then he gains 2 successful cakes, and his probability goes back to 0. So we're going to see again that we have 2 plus E0 in this term. And so now we have a system of 3 linear equations in 3 variables, which are E0, E0.5, and E1. And just to make our lives simpler, I'm going to rename E0 to A, E1 to B, and E2 to C. And once we write these equations out, we're going to get, this one becomes A equals 3/4 B plus 1/4 A plus 3/4. The second equation is going to become B equals 3/8 A, 3/8 C, 3/8 C plus 1/4 A plus 3/4. And our last equation is going to become C equals 1/4 A plus 3/4. There's no E2. So these things represent the expected value, the expected number of successful cakes that Gary will bake, given that he currently has a probability of 0 of giving up, or in this case 0.5 of giving up, or in this case a probability of 1 of giving up. So there's not going to be an E2 because he's never going to get to a probability of 2 of giving up. Oh, I see. Yeah. Sorry about that. I see what you're saying. These are supposed to be E0.5 and E1. Yeah, so thank you for catching that. All right, so from here, we get our 3 equations in A, B, and C. And so from here, we can solve this system of equations. So this is going to become 8B equals 3C plus 2A plus 6. And this is going to become A equals 4C minus 3. And by plugging this into that, B is equal to 4C minus 4. And then we can plug in both A and B back into this equation to solve for C. And C turns out to be 32/21. And then from C equals 32/21, we can solve for A, which is 4C minus 3. And that gives us an answer of 65/21. So 86 is the correct answer. All right, are there any questions? All right, so if there are no questions, let's move on to the last problem. So as usual, 5 minutes until we start going over the solution. And the solution to this problem is also going to involve states. So it's going to be kind of similar to the problem that we just did. All right, it's been around 5 minutes now, and let's start going over this problem. So we see that a string of digits from 0 to 9 is valid if the following conditions hold. First, for k between 2 and 4 inclusive, no run of k digits sums to a multiple of 10. So that is saying that no consecutive 2 digits sum to a multiple of 10, no consecutive 3 digits sum to a multiple of 10, and no consecutive 4 digits sum to a multiple of 10. And so let's just draw out, say, 4 consecutive digits, and let's say the first 3 are A, B, and C. Then our fourth digit cannot be congruent to negative A minus B minus C mod 10. And this is basically saying that this fourth digit, when added to the 3 digits that came before it, it cannot be 0 mod 10 or a multiple of 10. And we can say the same for a group of 3 digits and a group of 2 digits. This last digit cannot be equal to negative B minus C mod 10, and also cannot be congruent to negative C mod 10. And we can also notice that if we're given a valid string of digits of 2020 digits, or any number of digits, A plus B plus C, B plus C, and C, these 3 values, or rather, these 2 values are not 0. Because if they were 0, then the string of 3 digits A, B, and C, or B and C, would be summing to a multiple of 10, which is bad. So these are both not congruent to 0 mod 10. The third one can be congruent to 0 mod 10. So just keep that in mind. So we want to find the last 4 digits of the number of valid strings of length 2020. So let's first find the number of valid strings of length 2020. And it turns out that the expression for this number is actually not that bad, but the process that gets there is a bit more obscure. So let's introduce some notation. So in a string, let's call the last 3 digits A, B, and C, where A is the third to last, B is the second to last, and C is the third to last. And in any valid string, we cannot have more than one of A, B, and C being 0, because if, let's say, these 2 were 0, then these 2 would sum to 0, which is bad, and so on and so forth. So we're gonna split our possibilities into 4 cases. So okay, yeah. So if C is equal to 0, we're gonna call this, or let's start with A. If A is equal to 0, let's call this X of n. So there's gonna be X of a number of valid strings, that sum to, sorry, not that sum, that have its third to last digit as 0. There's gonna be Y sub n that have their second to last digit equaling 0, and Z sub n that have their last digit equaling 0. And if A, B, and C are all not equal to 0, then there's going to be W of n ways. And we can see that the number of valid strings of length 2020 would be Wn plus Xn plus Yn plus Zn. So let's just call the number of valid strings of length n to be, let's say, T of n. And then T of n is going to be equal to W of n plus X of n plus Y of n plus Z of n. And we want to go through these states just to see what equations we can get. So first of all, if we have a 0 in the third to last digit, then we can choose the remaining digits the way we want to, given that A, B, and C in this new string are not equal to 0. So we're going to get that X of n is equal to W of not W of n minus 1, Y of n minus 1. And then there's going to be 7 ways to choose the last digit. So there's going to be a 7 at the end. And let's go through this in a bit more detail. So let's say we have a valid string where the third to last digit is a 0. Then we can consider this string and also this last digit separately. So given the last 3 digits, there are going to be 7 ways to choose the last digit, because the last digit could be equal to 0. And so what we're going to do is, so let's say these 3 digits are called R, S, and T for lack of a better name. We used A, B, and C earlier. So this last digit cannot be congruent to negative T, negative S minus T, which also happens to be negative T, or negative R minus T. And both of these are different because R cannot be 0. If R is 0, then we have 2 consecutive digits which are both 0, and that'll give us a consecutive run of 2 digits that sums to a multiple of 10, and that's bad. And again, we also have that this digit is not 0. Right, we cannot have this digit being 0. So there's going to be exactly 7 possible digits from 0 to 9 that we can choose for our last digit. So X of n is going to be equal to Y sub n minus 1 times 7. That's going to be our first equation. Now we can do something similar with Y sub n. Y sub n is if we have a 0 in the second to last digit. And this would give us, again, 7 choices for our last digit. And Zn minus 1 ways to choose the remaining digits over here. The remaining n minus 1 digits that are not the last digit. And this is going to give us the equation Y of n is equal to Zn minus 1 times 7. And you can go through similar analysis for W of n and Z of n to get the equations. Z of n is equal to W of n minus 1, and W of n is equal to 6 times W n minus 1 plus 7 times Xn minus 1. I'm going to spare the details for now. But these are the equations that you get after going through the analyses of each of these 4 possibilities. And as we can see, Tn, which is the total number of valid strings of length n, is written as the sum of these 4 things. So we want to see what nice things can happen if we sum these 4 equations. And in fact, nice things do happen, as the left-hand side becomes T of n, and the right-hand side becomes 7 times Wn minus 1 plus 7 times Xn minus 1 plus 7 times the Yn minus 1 plus 7 times Zn minus 1. And that's nice because that's just equal to 7 times Tn minus 1. And so now we can create a really simple equation, a really simple closed form of this number of valid strings Tn. But currently we have a recursive equation. We can get Tn based on Tn minus 1. So we want to change that. We want to find, say, T3. Because, of course, throughout the steps that we've gone through so far, we're assuming that our valid string has at least 3 digits. The third to last, the second to last, and the first to last. So we cannot start with something that's T2 or T1. We must start with T3 or T4 or something larger. And so let's just calculate what T3 is. So by calculating T3, we can find that T3 is equal to 720, and this is by just picking the digits one by one. We're gonna have 10 ways to choose the first digit. We're gonna have 9 ways to choose the second digit, because these two digits cannot sum to 10 or 0. And then we're gonna have 8 ways to find the third digit, because we cannot have the third digit and the second digit summing to 10 or 0, and we cannot have the third digit, the second digit, and the first digit summing to 10 or 0. So that's going to give us a total of 720 ways to create a valid string of length 3. And so plugging this into our equation, we get that by way of geometric sequences, Tn is equal to 720 times 7 to the power of n minus 3. And so by plugging this into our, by plugging 2020 in for our n in this equation, we find that T of 2020, which is what we want to find, is equal to 720 times 7 to the power of 2017. And we're not done yet. We want to find the last 4 digits of this number. So if we go back to number 3, we can find the last 4 digits of a number by taking mod 10,000 of the number. And to take mod 10,000, we must, in this case, it would be helpful to use Chinese remainder theorem, since we're dealing with some very large numbers in the exponents. We're going to take mod 16 and mod 625. And we get these numbers because the prime factorization of 10,000 is 2 to the 4th times 5 to the 4th. So we can actually write these as mod 2 to the 4th and mod 5 to the 4th to spare any confusion. That's 4. And let's first take mod 2 to the 4th. So 720 is a multiple of 16. So this whole number is a multiple of 16, which means that this number taken mod 2 to the 4th is 0. And next we want to take this thing mod 5 to the 4th. And one thing we can notice is that 7 to the 4th power is equal to 2,401. And this is something that's really useful, because 2,401 is congruent to 25 plus 1 mod 125. So we can rewrite 7 to the 4th as 25 plus 1 mod 5 to the 4th, mod 5 cubed. Let me just write it this way. 7 to the 4th is congruent to 2041, which is congruent to 25 plus 1 mod 5 to the 4th power. And from here, you can use binomial theorem to find that, in fact, 7 to the power of 16, after canceling out all the stuff that have powers of 5 greater than 5 to the 4th power, we're going to get that 7 to the 16th is 25 plus 1 to the 4th. And this is congruent to 101 mod, this is mod 5 cubed, not 5 to the 4th. And then we can continue to find that 7 to the 17th power is congruent to 707. And we're just going to leave that as is for now. And let's come back to 7 to the power of 2017. So by Euler's theorem, which says that we can mod out phi of 5 to the 4th power from the exponent, and so phi of 5/4 is actually 500, which means that we can mod out 500 from the exponent and make this congruent to 7 to the power of 17 mod 625. And then we can find that the thing we want to find is actually congruent to, let me erase this to get more space. So we've already found that 7 to the 17 is congruent to 707 mod 200, mod 125. That means that if we take this thing, mod 625, we get that it's congruent to 720, which becomes or not 720. 720 is equal to 144 times 5 times 7 to the power of 2017. And since 7 to the power of 2017 is congruent to 7 to the power of 17 mod 125, which is congruent to 707, this means that 5 times 7 to the power of 2017 is congruent to 5 times 707 mod 625. And then to find this thing, T2020, which is 144 times this thing, mod 625, we simply want to find 144 times 5 times 707. And if you do the calculations, you get that it's 290 mod 625. So this is just some brutal calculations in this part by using Euler's theorem and also calculating some of these values by hand. And we're just going to note this here. This is 290 mod 5 to the 4th. And once you take Chinese remainder theorem, you can notice that mod 10,000, this is going to yield us 9,040 mod 10,000. You can check this because 9,040 taken mod 2 to the 4th is 0. So 9,040 is divisible by 16, and 9,040 is also 290 plus 5 to the 4th times 15. Sorry, 5 to the 4th times 14. And so this number is going to be the unique number that is congruent to T2020 mod 10,000. And so the last 4 digits of the number of valid strings of length 2020, which is T2020, is 9040, and that is our final answer. All right. So that last problem was kind of a tricky one, but yeah. Okay. Any questions? If there are no more questions, that's it for today. So thank you all for joining today's LogiSum Math Workshop. If you would like to see more of these workshops in the future, you can visit our website at logisum.club. I'll be signing off for today. So thank you, and hope to see you at our next workshop. Bye-bye.